All right, so now we're going to be talking about gauge interactions, right? So this one is actually going to be pretty short. It's actually not that complicated to show that we're interested again. What we're looking at, we're looking again at spikes in our field, and these spikes in our field are potentials where we have a delta function, okay? So, and we're going to do this for these four vector fields, right? The four vector fields that are described by our A mu, right? From our Lagrangian formalism on gauge fields. And these gauge fields, again, they contain these objects that we call electromagnetic field tensors, which was these F mu nu objects. And it was a combination of these and these objects, right? And we were able to show the Lagrangian in terms of just these objects, okay? And our equation of motion that came out of that was, again, a differential equation that told us how the system evolved. So let's talk now about this differential equation with the delta function, right? So the delta function again is x mu minus y mu. And in this case, what we have is the Minkowski metric equals d sigma a special function, again, rho sigma, right? This Minkowski metric, again, comes from a derivation that I don't think we covered, but basically what's going on here again is we have these special functions generating a spike, okay? And this was this here is our equation of motion. Again, sorry, I'm not one with words. This is our equation of motion that came out of our Lagrangian formalism again when we came forward with the Euler-Lagrange equations. And when we perform these Euler-Lagrange equations on our equation of motion, we get this Minkowski metric out, okay? And that might be something worth for a different video, or for a different video. What I want to do is really just show that I want to show that we're going to make a proposition for what these things look like. And we are going to take a look at how this satisfies this. So our proposition is going to be, again, a sum over momenta to the fourth e to I k mu x mu minus y mu, and then minus k mu eta rho gamma. Now the reason we have this Minkowski metric in here is because because the difference between our spinors and our vectors is that our spinors, again, they looked like this, where the objects in here, where these four component objects in here did not depend on where they were in space. All that these things really were components. Whereas these objects, whereas these objects here for the case of the 4 vector is that these things do depend on space-time, and so we need something that encodes the space-time in here so that we have that dependence, and that dependence is coming from the Minkowski metric. Again, we can, I can't remember if I actually derived this or not. I think I did, but if I didn't, then that might be something for a separate video. But this is the equation of motion that comes out of our Lagrangian, or Procol-Lagrangian, right? So what we can do is, again, we can really just move a few things. We'll move our integral inside, okay? And then we will move what we really get now is just this. When we perform our integration, we're just going to get our momenta vectors out, and everything else is pretty much just going to stay the same. So what I'm going to do here is just copy paste. Okay. And we can see already these things cancel. Okay. And what we get is all of this times this, which is this times this. Okay. That was it. You know, the long version of this would have been to derive this, but that again is, we've kind of covered it already. So, you know, we kind of covered it because we derived the equation of motions that came out of the Lagrangian, and you can go back to that video. So I don't know why I'm beating myself over the head on this. If you want to see it again, then perhaps you can go onto my Patreon page and make a request for that. But for right now, we're saying now that that this proposition works. It satisfies our equation of motion, right? So let's really quick review, because I'm realizing now that this is the last video that I'm probably going to make on chapter 5. And chapter 5, I think, is the second biggest chapter in the book. Again, the book that I'm following, at least, is this one right here, No Nonsense Quantum Field Theory. Chapter 5 was a big chapter. And so what we want to do now is perhaps talk about a summary. So I have notes here, and I'm going to go back in my notes, and I'm going to search for our Lagrangians that we've established. Okay, so here's our review. And what I'm going to plan on doing is putting perhaps an overview or of sort of chapter 5 in my Patreon page so that you can follow along there if you'd like also. So for our Klein-Gordon Lagrangian, we had 1/2 d mu phi minus m squared phi squared. Here we have, and for our Dirac Lagrangian, we had, let's see, just to make sure I don't get it wrong here. Sometimes, here we go. So for our Dirac Lagrangian, we had this guy here Okay. And for our Proca Lagrangian, the Proca Lagrangian looked like this. F mu nu plus m squared a mu. So these are our big boy Lagrangians. Right? We had our Dirac, not our Dirac, but our Euler-Lagrange equations, which went as follows. Right, and we were able to apply that to our fields. Okay, and then we had our equations of motion, so we were able to take our Lagrangians, feed them into the Euler-Lagrange equation, and get our equations of motion. And our equations of motion, again, were our Klein-Gordon equation, our Dirac equation, and our Proca equation. Right, so our, let's say our Proca equation for right now, let's just talk about that one because that's the one that's in front of me right now. Let's talk about, so our Proca equation was d plus m squared a rho equals 0, right? And then our Dirac equation was I gamma mu d mu. Actually, that was the other way around. I'll do it the other way around. Minus I gamma d mu gamma mu minus m equals 0. And then our Klein-Gordon equation was our Klein-Gordon equation looked like the following here: d mu plus m squared equals 0. Okay. So our Euler-Lagrange equation gave birth to our equations of motion. These are our equations of motion, and we were able to go forward with those, right? So this was our Proca. This dealt with 4 vectors. This was our Dirac. This dealt with spinors. And this was our Klein-Gordon, which dealt with scalars. And that is our review. So in this video, we've basically shown what all of our Green's functions were. We've shown, and we went over a review, basically a mini review of chapter 5. And so this video is short. I'm pushing on 15 minutes here, which is fine. But I think this is a good place to stop for chapter 5. We've gone over a lot. We've covered quite a bit on classical field theory. And again, classical field theory is vitally important for understanding quantum field theory, because once we're able to establish and understand what these classical fields look like, what the interactions look like in these fields, then it's going to be so much easier to understand quantum fields. Okay? Again, if you like this content, please subscribe. If you don't like this content, then don't subscribe. And if you want to contribute to this cause of teaching all you guys advanced physics, then go onto my Patreon page and make the donation of your choosing. With all that being said, I wish to see you guys in the next one. And yeah, well, in the next one, we're going to talk about review on quantum mechanics.